Hi guys, I've been getting a lot of questions about the conservation of energy, law of conservation of energy, and parabolic motion. So what I thought I'd do is I'd make up a question which combines all of those topics. So if you can follow this question from beginning to end, then you've got those two topics under control, and I'd suggest moving on to something else. So the question is, Derek has just been given a brand new Matchbox car. Because Derek is a spoilt brat, he immediately tries to find the best way he can break it. He builds a jump with dimensions shown below. Just before he hurtles his car down the ramp, you step in and recommend he places a pillow d meters away from the 20-degree incline where the jump ends. If he is going to push his car down the ramp at 0.5 meters a second, and in an attempt to save time you ignore the effects of friction and air resistance, how far away should you place the center of the pillow from the ramp? So we, in the end, are going to try and work out what D is equal to. So the Matchbox car will fly down this ramp, launch off the jump, and then land nicely in the pillow. So the way that we're going to do this first, let's break the question down into, there's going to be two sub-questions here. The first question we have to figure out is how we've got to figure out what his launch velocity is going to be from here. So we've got to figure out what that is going to be equal to. So let's go about working that out. So we've got to try and find this V here. So the way we're going to find this V here is using the law of conservation of energy, which states that energy cannot be created or destroyed. It can only change its form. So in this case, the change in form is going to be, because we haven't got friction or air resistance, the change in form is simply going to be between potential and kinetic energy. Okay, so to start this question, we have to work out what his total energy is at the top of the ramp when he pushes the car. So we're going to have to figure out his energy here. So what we'll do is we'll start this question down here, number 1, and we'll go, all right, his energy total up the top of the ramp is going to be equal to his kinetic energy plus the car's potential energy. Pretty straightforward. So what we can do now is from here we then go, all right, well, his kinetic energy, we start putting in our formulas, is equal to 1 over 2 half mv squared. And his potential energy is equal to, so we're going to add whatever potential energy the car has, mgh. Now, I don't know if you guys have realized this already, but we're not given what the car's mass is. Now, that's not going to be a problem, but some kids would start to freak out because they can't put in a mass. So what we're going to do is we're going to show you why it's not a problem as well here, so you can, go forth without freaking out, to be perfectly honest. So what we're going to do is we're going to divide or factorize this entire, I'm getting ahead of myself, this entire function here by m. So we're going to go, this is going to be equal to m outside of 1 half v squared plus gh. Cool. So basically we're going to have a total energy in terms of m. So what we do is we sub in the numbers that we know. So we've got, this is going to be equal to m outside of 1 half times his velocity, which at the start is 0.5, squared, plus 9.8, which is g, or 9.81, times his height, which is 1.2. Now, if we do all that maths, we are going to pop out with a number 11.897 inside the bracket, and that's being multiplied. That's the worst equals sign ever. 11.8 0.997, and that's being multiplied by m. Cool, so we'll just call it, now that would be measured in joules as well, because that's energy, so I'll just put it in brackets here. So, now, once we've got that, we need to figure out what his energy is going to be here, because that's going to tell us what his velocity is. We'll be able to solve for velocity. Okay, well at 2, we have the same situation. So we have 2. His energy total is going to be equal to the sum of his kinetic energy plus his potential energy. Cool. Now, we can take this into factorized form first. So we can instead of being like writing this one out again, let's go straight to this one here, because that's going to make it a lot more simple. So this is equal to m outside of 1/2 v squared plus gh which in this case is going to be equal to, and this has got to be equal to the total energy, which we derived in 1, because the law of conservation of energy states that the energy at 1 has to be equal to the energy at 2. So this has got to equal 11.897. m. Cool. So now what I'm going to do is, before I substitute in my numbers, you can see that I've got an m on both sides. So what I'm going to do is I'm going to divide both sides by m, just do a little bit of algebra. And what happens here is the m's cancel, which is quite handy, to be honest. So we then substitute our numbers in. We've got 1/2 v squared. Now this v is what we're looking for, because that's going to be equal to that v, plus g, which is 9.81, times height, in this case is 0.2, and that's got to be equal to 11.897. Cool. So what we know is, we know that 9.8 times 0.2, if you put that into a calculator, you'll get 1.962. So what we can then do is, let's just rearrange this, and we're going to have v is going to have to be equal to the square root of 2 times 11.897 subtract 1.962. Close that bracket. And so that 1.962 came from the 9.81 times 0.2. And that's got to be equal to 4.458. Cool. So that's the first half of the question done. We've figured out what his velocity is going to be at when the car launches off the ramp. All right. So that was our law of conservation of energy part of the question. Now we've got to go into the parabolic motion part of the question. So basically, when you're doing any parabolic motion question, what you want to do is you want to draw a basically a vector triangle, so you can get the horizontal and vertical components of this velocity. So we're going to do that. So I'm going to get a, yep. So here we go. We're going to draw a line here. We're going to draw a line up here. And we're going to draw a line down there. Cool. Now let's go back to our thing. That's a right angle here. Now it says our launch ramp is 20 degrees. So that's 20. And we know that his launch velocity is 4.458. We just worked that out. And that's meters per second to the -1. Cool. So I'm going to change colors so you can see what I'm doing. All right. Now, the first thing I do, even if I don't think I'm going to use, like, if I'm in two minds whether I'm going to use it, I think it's good form to work out what both the horizontal and vertical components of this velocity are going to be. You do both of them straight away. So I'll start with the horizontal one. So this is going to be the velocity horizontal. Cool. And that's good. This is the adjacent side. Hypotenuse, it's going to be cosine, so it's going to be 4.458 times the cosine of 20 degrees. And that's going to come out with a number 4.189. meters per second. And the force in the vertical direction, we've got, or the velocity, sorry, in the vertical direction is going to be equal to 4.458 times the opposite and hypotenuse, the sine of 20 degrees. And that equals 1.525. Great. So now we've got our two components of the velocity. So now what we're going to have to do is we're going to have to figure out, well, what has to happen now? Well, we have to, in the end, the way that we work out this distance is we need to figure out the total time that the Matchbox car is going to be in the air. Because once we know the total time it's going to be in the air, we can then just multiply the time by the velocity in the horizontal direction, and that'll give us that distance there. So the way we do that is we break down this parabolic motion, because what we're going to have is it's going to, the parabola is going to look like this. It's going to go up, and then it's going to go down. So what we're going to do is we're going to work out the time that goes from the launch ramp to the top of the arc, or top of the parabola, and then we're going to work out that time, and then so that's going to be one time, and then we're going to work out the time that it takes to go from, hang on a sec, time it takes to go from the top all the way down to the bottom. So these, we'll call these T1 and T2. Okay, so what we're going to have to do is to work out T1, we'll just change colour because that green is incredibly hard to read. We'll go back to blue. So what we're going to start with is we're going to work out what the distance is from here to the top. So the way we work that out is we can go use the formula v squared equals u squared plus 2as And what we can rearrange this, I'm not going to show you how to do the algebra, but when we substitute in v squared, which is the vertical component of our velocity, well, sorry, that's going to be our u squared. Our v squared, the velocity at the top of the arc is going to be equal to 0. U squared is our initial velocity, which is the vertical component of our launch velocity. We've got the acceleration, which is going to be in the opposite direction to the launch velocity. So that's going to be negative 9.81, and we're trying to figure out what s is. So if you substitute all those in, we get 0 equals 1.525 squared plus 2 times negative 9.81 times the distance. And after we rearrange that, we get a distance of 0.118 meters. So what we also need to work out is so we are going to be using that distance to calculate time 2. So to calculate time 1, we're going to use the formula. So let me just draw a little line there. We're going to use the formula V equals U plus AT. Now the velocity is 0. The horizontal launch velocity is 1.525. The acceleration is negative 9.81, and the time is what we're looking for. So if you rearrange that, we can get the time equal to 0.1. Great. So what we need to now calculate is we need to calculate T2. So that's T1. Let's write that down. T1 is that. Now to work out T2, we're going to use the fact that it's got to travel the distance of 0.118 meters plus this 20 centimeters that we have to launch off, because the distance from the ramp to the top is going to be less than the distance of the top to the pillow. So what we're going to then do is we're going to go, okay, so we're going to use the formula S is equal to UT plus 1/2 AT squared. And we know that the distance has to be equal to the 20 centimeters plus the 0.118 meters that we've got there. So this is going to be equal to 0.318 meters. Sorry. And that's equal to the U, because the initial velocity here when we're at the top of the parabola is 0, that's going to cancel that entire term out. So we've got, this is going to be equal to 1/2 times 9.8 times t squared. Now, if we rearrange that, we get a t value is equal to 0.255 seconds. Cool. So, we'll continue this underneath here because there's not much to go. So what we now know, let's make a little line, we need to work out our time total. And that's going to be equal to T1 plus T2. And that is equal to 0.41 seconds. Cool. So then what we can do is we then go, all right, the Matchbox car is going to be in the air for just a bit less than half a second. We know that its horizontal velocity is equal to this. So we're going to use the formula distance is equal to velocity times time, which is going to be equal to the velocity 4.189 in the horizontal direction times the time 0.41, and that gives us a distance of 1.72. So what we found out is that we have to stick the center of the pillow 1.72 meters away from the launch ramp. And that's assuming also that the pillow is at the same level as the floor, which is a fairly bad assumption to make, but you know, to like not add another layer of complexity to it, the pillow has to be at the level of the floor, and it needs to be 1.72 meters away from the edge of the launch ramp. So if we're going to recap, this problem was broken down into two sections. The first section was using the law of conservation of energy to calculate the launch velocity of the Matchbox car at the end of the ramp here at 2. So to do that, we use the fact that energy cannot be created or destroyed, and because the car in its trajectory down the ramp and launching it doesn't change its mass, we don't really need its mass. We can see that the masses cancel. So that's a fairly it's a fairly common sort of cause for concern for a lot of kids when they say, oh, they haven't given me any mass. Well, to be honest, it doesn't really matter. So once we figured out what its velocity was, we then had to work out what the horizontal and vertical components of that velocity were. Once we worked that out, we then used the vertical component of the velocity to work out, first of all, how high the car went above the launch ramp and how long it took to get from the launch ramp to the top of the car's trajectory. We then used the height of the car at the top of the trajectory plus the height of the launch ramp to figure out how long it was going to take to get from the top of the trajectory to the pillow. We then added those two times together and then multiplied that resultant time by the horizontal component of the Matchbox car's velocity to give us what the horizontal distance needed to be from the launch ramp to the pillow. So it's a fairly long question, but not really that complicated once you sort of can break it down into its smaller sub-problems. So I hope that video helped, and I'll see you next time.